This video looks at multiplication as a linear transformation investigation. So I'm going to guide you through an example from the Pearson textbook. Now, on the Argand plane, point A is defined by the complex number u equals 3 plus I. So you can see that drawn just here. Okay, and B is the point defined by the complex number v, which is 4 plus 4i. So our first step is to calculate the line segment of AB. You can see down that down the bottom using Pythagoras' theorem. So all they've done is drawn the right angled triangle here, noting that that is y2 minus y1, which is your 4 minus 1, and this here is your x2 minus x1, which will be your 4 minus 3. Now, interestingly, I'm going to do a side note here and think about it like vectors. When you needed to find the vector AB, you went B minus A. So let's think about that. If we have the coordinate 4, 4, and we minus 3, 1, you end up with 4 minus 3 is 1, 4 minus 1 is 3. And then to find the length of AB, the modulus of it, you would use Pythag. So you got 1 squared plus 3 squared, which is the square root of 1 plus 9, which is the square root of 10 units, which is the same answer. Okay, so complex numbers no different to what we did in vectors. Now, let's look at the transformation. The transform point A, or A dash, and B are created by multiplying complex numbers u and v by z equals 1 plus I. So our u, which was our 3 plus I, we're going to multiply that by 1 plus I. And you can see that calculation there. And then your v, which is 4 plus 4i, is multiplied by 1 plus I. And you can see that calculation there. So our transformed A becomes a 0.24 and our transformed B becomes a 0.08, which you can see on this Argand plane. So the next step is to work out the length of the transformed AB. So we're looking at this length here now. So again, you could draw a right angle triangle. This length here would be 8 minus 4, which is 4. This length here would be 2 minus 0, which is 2. So you have the square root of 2 squared plus 4 squared. Okay? Or you can think about it again as if we have the vector AB, that's going to be B dash minus A dash, which is 0, 8 minus 2, 4, which is negative 2, 4. And then to find the length of that would be the square root of negative 2 all squared plus 4 squared, which is the square root of 4 plus 16, which is a square root of 20. And that's units. Now, we found out before that the length of AB was a square root of 10 units. So comparing these two, we can say that the length of A dash B dash is the square root of 2 times by the square root of 10. Or square root of 2 times by the length of our AB. Okay, so you can see off to the side I've written here, or from the textbook, that multiplying by the complex number 1 plus I increase the magnitude of length by the square root of 2. Okay, well, let's look at 1 plus I. If we have z equals 1 plus I, what's the length of that vector? So again, what's the length of that complex number, which is still a vector? Okay, so we're thinking about it on our plane. We have 1 plus I here, which is the point 1, 1. Okay, so that's going to be the square root of 1 squared plus 1 squared, which is a square root of 2. So our transformed AB line segment is multiplied by the modulus of z. Okay, the other thing that happens to it, if you look at our original diagram, okay, that's your A and that's your B, okay, your original. So if we look at AB compared to the transformed AB, that's been rotated anti-clockwise 45 degrees. Okay, so that's just a little investigation to see the effects of dilation and rotation. So when multiplying by a complex number a plus bi, you're multiplying by the modulus and you're also rotating.